Hey everyone, today we're diving into a groundbreaking paper titled ATOM, a method for stochastic optimization. This is the algorithm that's revolutionized how we train deep learning models, so stick around to learn how it works. Ever wondered how to make optimization algorithms smarter and faster? ATOM is here to save the day. It's a first-order gradient-based method that uses adaptive estimates of moments to handle noisy objectives efficiently. Imagine it as a smart coach that adjusts learning rates for each parameter individually, making it great for large-scale problems with sparse or non-stationary data. Plus, it's easy to implement, memory-friendly, and requires minimal tuning. No wonder it outperforms other methods in practice. We'll also touch on ATOMax, a cool variant based on the infinity norm, later on. Why is stochastic optimization such a big deal in fields like machine learning? Well, many real-world problems involve optimizing functions that are noisy or based on subsets of data. Gradient descent is efficient because computing derivatives isn't much harder than evaluating the function itself. Stochastic gradient descent, or SGD, takes this further by using random data samples, which has powered huge advances in deep learning. But when objectives are noisy due to things like dropout or data subsampling, we need robust methods. That's where ATOM comes in, focusing on high-dimensional spaces where simpler methods fall short. So what makes ATOM so special? It's an adaptive optimizer that calculates custom learning rates for each parameter by estimating the first and second moments of gradients. Think of it as giving each parameter its own personalized training pace. ATOM combines the best of ATOGrad, which excels with sparse data, and RMS Prop, great for changing environments. Key perks include being invariant to gradient scaling, having bounded step sizes, and handling non-stationary or sparse gradients effortlessly, all while automatically adjusting step sizes over time for smoother convergence. All right, let's dive into the ATOM algorithm. Imagine you're trying to find the lowest point in a hilly landscape, but it's foggy and you can't see clearly. That's like optimizing a noisy function. ATOM helps by keeping track of two things: the average direction you've been moving and how bumpy the terrain is. It uses these to adjust your step size automatically so you don't overshoot or get stuck. The default settings, like a learning rate of 0.001, are like starting with a safe, steady pace that works well for most machine learning tasks. All the math here is done element by element, meaning each parameter gets its own custom treatment, which is super efficient for big problems. Here's the step-by-step breakdown of ATOM in action. You start by initializing some vectors to 0. Think of them as blank slates for tracking your moves. Then, at each step, you compute the gradient, which is like feeling the slope under your feet. ATOM updates two running averages, one for the gradient itself and another for its square, kind of like remembering your recent steps and how erratic they were. But wait, there's a catch. These averages are biased at first because they start from 0. So ATOM corrects for that bias to give you a clearer picture. Finally, it updates the parameters by taking a step that's scaled by these corrected estimates, ensuring you move smoothly towards the minimum without wild swings. In the upcoming sections, we'll explore why ATOM is such a game changer. First, we'll look at the algorithm's core mechanics and what makes its update rule special. Then, we'll dive into how it fixes that initial bias, which is crucial for getting accurate results early on. There's even a theoretical part showing why ATOM converges reliably in complex settings. And the best part? In tests, ATOM consistently beats other methods across different models and datasets, proving it's a powerhouse for tackling large-scale machine learning challenges. So what's ATOM all about? It's designed to minimize a noisy objective function, which is common in machine learning when you're dealing with random data samples. Think of it like trying to find the average trend in a chaotic stock market. You want to smooth out the noise to see the real direction. ATOM works by computing gradients at each step, which are just the slopes indicating where to go next. These gradients help it adaptively adjust how big each step should be, making the optimization process much smarter and faster. Now, here's where it gets clever. Atom maintains exponential moving averages of the gradient and its square. Why? To estimate the mean and variance of the gradients over time. But if you start these averages at 0, they're biased, like assuming you haven't moved at all when you actually have. This bias is worse early on, but Atom has a neat trick to correct it, giving you unbiased estimates that lead to more stable updates. We'll cover that correction in detail later, so stay tuned for how it makes Atom so effective from the get-go. By the way, the algorithm can be tweaked for better efficiency without changing how it works. For example, you can rearrange some calculations to speed things up, though it might make the code a bit harder to read. It's like optimizing a recipe. You can prep ingredients in a different order to save time, but the final dish still tastes the same. Let's talk about Atom's update rule and why its step size is so well behaved. The effective step size is automatically bounded, meaning it won't let you take huge, risky jumps that could derail your progress. Imagine driving on a winding road. Atom ensures your speed adjusts based on the curves, so you never go too fast and crash. This property helps maintain stability during training, especially when gradients are noisy or unpredictable. Ever wondered how Atom handles super sparse data where gradients are mostly 0? Well, in the worst-case scenario, if a gradient is only non-zero at the current step, Atom's step size can be large. But for less sparse cases, it shrinks down. Why does this happen? Atom uses a ratio called signal-to-noise, which compares the average gradient to its variability. When this ratio is high, you're more confident in the gradient direction, so steps are bigger. But when it's low, like near an optimum, steps get smaller automatically, kind of like a built-in annealing process that prevents overshooting. Plus, Atom's step size is bounded by the learning rate you set, creating a trust region that keeps updates stable. This makes it easier to pick a good learning rate up front, especially since we often know roughly where the best parameters lie in machine learning models. Now let's dive into how Atom fixes initialization bias. Remember, Atom uses exponential moving averages for gradients and their squares, but starting from 0 can skew things early on. For the second moment, which estimates the variance of gradients, Atom tracks it with a decay rate. By looking at past gradients, it builds this average step by step. The key insight is that without correction, the expected value of this average doesn't match the true variance at first because of that 0 start. So Atom applies a fix to make sure the estimates are accurate from the get-go. This formula shows how the moving average is a weighted sum of past squared gradients, with older ones having less influence due to the decay. It's like smoothing out the noise to get a clearer picture of gradient behavior over time. To correct the bias, Atom compares the expected value of this average to the true second moment. By taking expectations, we see a discrepancy caused by initializing with zeros, which Atom addresses by dividing by a correction term. This ensures the estimates are unbiased and reliable, especially important in the early stages of training. This part simplifies the expectation calculation, showing that the corrected term helps align the moving average with the true gradient variance, assuming things are mostly stable over time. So why does this bias correction matter? If the true variance isn't changing much, the correction term handles the initial 0 bias neatly. But even if it fluctuates, picking a good decay rate keeps the average focused on recent gradients, minimizing errors. In Atom's algorithm, dividing by this term makes those early steps much more accurate. Without it, you could end up with huge, unstable updates right at the start. And here's the kicker for sparse gradients. To get a reliable variance estimate, you need a small decay rate to average over many gradients. But without bias correction, that small rate would cause massive initial steps. Atom's fix prevents this, making it robust even in tricky sparse scenarios.
We are Genipad, Your likes and subscriptions inspire us to create more videos and keep improving our service. Want to turn your own content into videos? Visit us at www.genipad.com.
Ever wondered how we can prove that Atom actually converges to a good solution? Well, in online learning, we're dealing with a sequence of unknown cost functions, and at each step, we predict parameters and face a new function. The key metric here is regret, which measures how much worse our predictions are compared to the best fixed parameters over time. Essentially, regret sums up all the differences between our online performance and the ideal one, helping us see if the algorithm improves steadily. To make things simpler, we define some notation. Gradients over time are grouped by dimension, and we use exponential decay for the learning rate and momentum. This setup ensures that Atom's updates are stable and efficient, especially when the learning rate decreases over time, which is crucial for handling noisy data without going off track. Here's the big theorem for Atom's convergence. It assumes that the gradients and parameter distances are bounded, which is common in practice to prevent extreme values. With specific settings for the decay rates, Atom guarantees a bounded regret, meaning it doesn't perform too poorly compared to the best possible outcome over many steps. The regret bound involves terms that account for the sum of gradients and their magnitudes over time. In simple terms, this formula shows that Atom keeps the cumulative error in check, thanks to its adaptive learning rates that adjust based on past gradient information. What's really cool is that for sparse data, this bound can be much tighter, leading to faster convergence. Adaptive methods like Atom and Adigrad can achieve regret that grows slowly, like logarithmically with dimensions, which is a huge win over non-adaptive methods that might scale poorly. Also, reducing the momentum over time isn't just a trick. It's backed by theory and helps Atom settle into a good solution without overshooting. Ultimately, this means that Atom's average regret gets smaller and smaller as training goes on, so it reliably finds better parameters over time. This corollary builds on the main theorem, showing that under the same bounded conditions, Atom's regret grows at a rate proportional to the square root of time. It's a straightforward result that reinforces Atom's stability and efficiency in optimization. By plugging in the bounds from the theorem, we see that the regret approaches zero as time goes to infinity. So Atom doesn't just work, it gets progressively better, ensuring long-term convergence in machine learning tasks. Atom isn't alone in the world of optimization. It's closely related to methods like RMS-prop and Adigrad. RMS-prop adjusts learning rates based on recent gradient magnitudes, while Adigrad does it cumulatively, making them great for non-stationary or sparse data. Other approaches, like VSGD and AdaDelta, also tweak step sizes by estimating curvature, but Atom combines the best of these ideas for robust performance across various scenarios. All right, check out this graph. It's comparing different optimizers like Atom, Adigrad, and SGD with Nesterov momentum on two datasets, MNIST for image recognition, and IMDb for text reviews. The lines show how quickly each method reduces the error, with Atom keeping up with Adigrad in speed. This visual really highlights why Atom is a top choice for fast and stable training. So what's the big deal here? This figure shows the training progress for logistic regression, where lower values mean better performance. Atom isn't just fast. It handles sparse data from the IMDb reviews effortlessly, proving it's robust for real-world tasks without needing extra tweaks. Ever wondered how to stop your model from overfitting? In this experiment, Adigrad beats SGD with Nesterov momentum by a huge margin, even with dropout noise added. Atom matches Adigrad's speed, showing it can leverage sparse features for quicker convergence. just as the theory predicted. It's like having a smart assistant that adapts on the fly to get you better results faster. Now, let's dive into multi-layer neural networks. These models have complex, non-convex goals that can be tricky to optimize. Even though Adam's theory doesn't cover this, it often beats other methods in practice. We used a network with 2 hidden layers and ReLU activations, similar to setups in other studies, to keep things fair and comparable. First up, we tested optimizers on a standard task with L2 regularization to avoid overfitting. SFO, a newer method, uses mini batches but is much slower, 5 to 10 times per iteration, and needs more memory. Adam, on the other hand, speeds ahead in both iteration count and real time, making it a clear winner for efficiency without sacrificing performance. What about stochastic tricks like dropout? They're great for preventing overfitting, but SFO can't handle them and fails to converge. Adam excels here, outperforming other stochastic methods and showing robust convergence. It's like Adam has built-in adaptability that others lack, making it ideal for practical neural network training. Convolutional neural networks, or CNNs, are superstars in computer vision, using layers like convolution and pooling to process images. Unlike standard nets, CNNs have shared weights that create varying gradients across layers, often needing careful learning rate tuning. Adam steps in to handle this complexity smoothly, as we'll see in this deep CNN setup with ReLU units and whitened inputs. Ever wondered how Adam stacks up against other optimizers in real-world tests? In Figure 2, they trained multi-layer neural networks on MNIST images. And here's the cool part. When they used dropout for regularization, Adam was compared to SFO. The graph shows how the training cost changes over iterations, giving us a clear picture of which method handles noise and complexity better. It's like watching a race where Adam adapts its pace automatically, while others might need manual tweaks. Check out Figure 3 for some eye-opening results on convolutional neural networks trained on CIFAR-10. On the left, you see the training cost in the first 3 epochs, where Adam and others start strong, but the right side shows the full story over 45 epochs. Adam and SGD, with momentum, eventually pull ahead of arXiv, proving that adaptive learning rates really shine in longer runs. It's all about how well each optimizer navigates the twists and turns of complex data without getting stuck. In this setup, they added dropout noise to the input and fully connected layers to simulate real-world uncertainty, and used a mini-batch size of 128 for consistency. Think of dropout as randomly silencing parts of the network during training, forcing it to be more robust, and Adam handles this chaos smoothly without extra fuss. Why does Adam outperform arXiv in convolutional neural networks? Initially, both drop the cost fast, but Adam and SGD speed up later on. The key is in the second moment estimate. It fades to near zero in CNNs, making it a weak guide for the cost function's shape. Instead, Adam focuses on reducing noise through the first moment, which is like fine-tuning the engine for better acceleration. So while arXiv lags behind, Adam's automatic layer-wise learning rates give it an edge without manual guesswork. Have you ever wondered how bias correction can save your model from early training chaos? In this figure, we're looking at a variational autoencoder, and it shows the loss over time with and without bias correction. The red line represents Adam with bias correction, while the green line is without it. After just 10 epochs, without bias correction, the loss can be all over the place, especially with certain hyperparameter settings. But after 100 epochs, bias correction keeps things stable, preventing those wild swings that could derail your training. This is crucial because, as gradients get sparser, bias correction ensures your model doesn't take huge, unstable steps early on. Let's dive into why bias correction in Atom is such a game changer. In this experiment, they tested Atom against a version without bias correction, which is basically RMS prop with momentum. They trained a variational autoencoder, tweaking hyperparameters like the decay rates for the first and second moments. When the second moment decay rate is set close to 1, which is needed for handling sparse gradients, the initialization bias becomes a big problem. Without bias correction, the model can go haywire in the first few epochs, leading to unstable training. But with bias correction, Atom stays robust, performing just as well or better across all settings, especially as gradients thin out later in training. So what did they find? In the figure, when the second moment decay rate is high, training without bias correction becomes unstable early on. The best results came with small values for 1, minus the decay rate and bias correction enabled. This was super clear towards the end of optimization, where gradients get sparser and models need that extra stability. In short, Atom consistently matched or beat RMS prop, no matter how they set the hyperparameters, thanks to that bias correction magic. Ever thought about taking Atom to the next level? Meet AtomX, an extension that tweaks the update rule. In standard Atom, it scales gradients using a kind of L2 norm, but AtomX generalizes this to an LP norm. For large P, things can get numerically messy, but when P goes to infinity, something cool happens. It becomes super simple and stable. This algorithm adjusts the step size based on the maximum of past gradients, making it even more robust in certain cases. Here's how it works. The update uses a term that combines the previous value with the current gradient's P norm. When P is infinite, this simplifies to tracking the maximum gradient magnitude over time, which helps in controlling step sizes without the instability that can come with high P values. This formula shows how the update accumulates gradient information over time, weighting recent gradients more heavily to adapt the learning rate dynamically. Ever wondered if there's a way to make Atom even more stable? Enter AtomX, a cool variant that uses the infinity norm to scale gradients. Instead of squaring gradients like Atom, it tracks the maximum absolute value over time, which simplifies things and can handle extreme gradient values better. For most machine learning tasks, the authors suggest default settings like a learning rate of 0.002, with decay rates of 0.9 and 0.999. Bias correction is still there for the first moment to keep updates smooth, especially early in training. Here's how AtomX works step by step. It starts by initializing vectors for the first moment and the infinity norm to 0. At each step, it computes gradients from the objective function, updates the first moment with an exponential average, and then updates the infinity norm by taking the maximum between the previous norm scaled by a decay factor and the current gradient's absolute value. Finally, it adjusts the parameters using a learning rate that includes bias correction for the first moment, divided by this infinity norm. This whole process repeats until convergence, making it robust and efficient for noisy data. Let's break down the math behind AtomX in a simple way. Imagine you're taking a limit as a parameter approaches infinity, which transforms the update rule into something much cleaner. Instead of dealing with complex averages, AtomX ends up using a straightforward recursive formula that picks the maximum value between a scaled previous state and the current gradient magnitude. This leads to a key insight. The update in AtomX is bounded by the learning rate, meaning the steps it takes can't get too large and cause instability. Plus, there's no need for bias correction here, which makes the algorithm simpler and more reliable right from the start. Why does averaging parameters help in optimization? Well, since stochastic methods like Atom can be noisy, Averaging the parameters over time smooths things out and often leads to better generalization. Think of it like taking an average of your guesses to get a more accurate final answer. You can do this with simple averaging or an exponential moving average that gives more weight to recent values, and bias correction ensures it's accurate from the beginning. So, what's the big takeaway? The authors have introduced ADAM as a straightforward and efficient optimizer for gradient-based problems in machine learning. It's designed to handle the noise and complexity of real-world data with minimal tweaking, making it a go-to choice for training models effectively. Ever wondered how ADAM handles those massive data sets and complex problems? It's like having a super smart assistant that learns from both AdaGrad and RMS Prop. AdaGrad is great for sparse data where updates are rare, while RMS Prop shines when the goal keeps shifting. ADAM merges these powers, giving you a tool that's easy to set up and doesn't hog memory. In tests, it proved its speed on straightforward problems and was a rock star across all sorts of tricky machine learning challenges, even the non-convex ones where the path isn't clear. Did you know that ADAM almost didn't get its name? Big shout out to the folks at Google DeepMind and others like Ivo Danahelka and Tom Schall for that. Also, quick thanks to Kai Fan for catching a mistake early on. The experiments ran on some serious Dutch computing power, and Diederik Kingma had Google's backing through a fellowship. It's amazing how collaboration fuels these breakthroughs.